Chapter 8 is about reactions of alkenes. So we learned about alkenes. We learned about the functional group, a CC double bond, where we have one sigma bond and one pi bond. We also know that the sigma bond is strong and pi bond is weaker bond, is a weaker bond. So compared to alkane, now we have part of the molecule, which is the functional group for alkene, that contains a pi bond, and that pi bond is not very strong. So that makes the alkene unique, and it can go compounds that they have alkene functional group. They could go to a type of reaction. They could go through a type of reaction called addition reaction. What is happening in addition reaction is that you are adding something to existing bond. So if, let's say you have an R group here. So you have, let's say you add hydrogen. Okay. So this is the same thing as the addition reaction or combination reaction you learned in general chemistry. When you're adding H2 to alkene, the molecule of the alkene, everything stays the same. The only thing is happening here, the pi bond is going to break, and the pi bond, it could break hemolytically or heterolytically. What does hemolytic means? It means that if you have a pi bond that breaks hemolytically, you're going to get this free radical on each carbon. That's hemolytic. Okay. For heterolytic cleavage of the pi bond, one carbon could take the plus charge and the other carbon could take the minus charge or pair of electrons. So basically, if the pair of electron moves toward one carbon, that is heterolytic. But in this case, for hemolytic, the pi bond is going to break and one electron to each carbon. And it could be, either one of them could be positive or it could be negative, because if they are, especially if they are symmetrical. So when you're adding hydrogen, then one hydrogen will be added to carbon and another hydrogen would be added to the other carbon. This reaction in general is called addition reaction of alkenes. So what is happening generally in the addition reaction is that you have two steps. In step one, you have electrophile coming in. Okay, you could have like an electrophile coming in because you have pair of electrons in the pi bond. So this area of the molecule is electron rich, and because it's electron rich, an electrophile, something that likes electron, can come in and form bond with this compound. So if you notice, the arrow is always from electron rich to electron poor. So I'm just drawing this one more time for you to see that is coming. I'm not doubling, I'm just drawing it again just for you to see it. It's going from electron rich to electron poor. E plus is electron deficient, pi bond is, or double bond here is electron rich area. Even though we call it that the electrophile is coming to form bond with the pi bond, but the movement is just based on the convention. The arrow is going from pi bond or from the pi electrons to the electrophile, always from electron rich to electron poor. So when electrophile comes in, what is happening a bond is going to form, a new bond is going to form between the electrophile and a carbon. So with the line that I'm marking red color here, that represents 2 electrons. Those 2 electrons did not come from electrophile, and electrophile did not bring any electrons. So what are those 2 electrons? Those are the 2 electrons that we had from the pi bond. So these are the pi bond electrons. The pi bond electron was shared between carbon 1 and carbon 2. Now, the pi electron, it moved down between electrophile and carbon 1. Okay, so what happens in terms of number of electrons for carbon 1? We had, before electrophile comes in, we had 2 electron, 2 electron, 2 electron, and 4 electron. Here, altogether, we had 8 electrons for carbon 1. How many electrons do we have for carbon 1 after the electrophile coming in? Is 2 electron, 4 electron, 6 electron, and 8 electron. So carbon 1 doesn't change in terms of the number of electron going from reactant to product side, or before adding the electrophile to after adding electrophile. But what is happening to carbon number 2? Carbon number 2 has lost pair of electron to carbon 1, or has given that up pair of electron to carbon 1 to form the bond with the electrophile. So carbon 2 has only 2 electron, 4 electron, and 6 electron. And if it has only 6 electron, it's electron deficient, and it gains a plus charge. So anytime you bring electrophile to carbon-carbon plus the electrophile, the product, on the product side, you are going to have 1 carbon bonding to electrophile, and any carbon that bonds to the electrophile, the other carbon will take the plus charge, because you are bringing electrophile with no electrons, and you do need 2 electrons to form this new bond here. So it takes the plus charge. So that's what the step 1 of the addition reaction. In step 2 of the addition reaction, a nucleophile comes in. When you say nucleophile, what does nucleophile mean? It means that it likes nucleus, either has pair of unshared electron or has a negative charge, and it likes nucleophile. So if it likes nucleophile, it's going to come and form bond with this carbocation now. So we have a second step, and that's shown in on this equation here, nucleophile attacking the carbocation, forming bond with carbocation. So what is happening here? You have a negative charge coming from nucleophile, a positive charge from carbocation, and these 2 positive and negative charge, they cancel each other's effect. If your nucleophile has negative charge already, the product is going to be neutral, and you have a product. But if your nucleophile, it's not negatively charged, if it's a neutral, then you are going to end up with a positive charge left over in the product, which is not a product yet. At that point, you will not call it product, you will call it still intermediate, until somehow you remove this plus charge. Keep that in mind until we get to those examples. Like if you have water as a nucleophile or alcohol as nucleophile, the plus charge is going to be then removed by the solvent or by base that you are going to bring in. So you have 2 types of the 2 steps of the reaction: electrophilic attack, or the pi bond attacking the electrophile, and step 2, nucleophile comes in and forms bond with the carbocation or nucleophilic attack. Those are the 2 steps of the reaction. Now, it depends on what you have as the electrophile and the nucleophile. Then your product is going to be more specific, and there are plenty of these choices here. So let's say if you have a CC double bond and you add HX, I'm going to make it more specific because you have H, let's say I add HBr. So if I look at the structure for HBr, Br is more electronegative than H. Br is partially negative and H is partially positive. So this side of the molecule, when it dissociates, is going to give me H plus, and the other side of the molecule is going to be Br minus. My Br minus in this reaction is classified as a nucleophile, and the H plus is classified as the electrophile. So I have my electrophile and I have the nucleophile. So when you add, electrophile is going to add to 1 carbon. And if that is the first step, so you are going to get the H added to 1, H added to 1 carbon. The other one takes the plus charge, and then the nucleophile comes in, and then the Br adds. So the net result of adding HBr, I'm going to get alkyl halide. Now, what happens if you add H2O? If you add H2O, basically, when you're adding H2O, so if you add H2O, that means you add H and add OH. Keep this in mind. When you're adding H2O, you're adding H to 1 carbon, 2 carbon-carbon double bond. When you're adding H2O, you're adding H to 1 carbon and OH to the other carbon. So what would be the product? The product is gaining hydrogen on 1 carbon, OH and another carbon. So in this case, you got alkyl halide. Now we are getting alcohol. So depends on what you're adding, your product is going to be different. There are a lot of reactions in this chapter, and that basically every reaction is going to follow the same pattern. Electrophilic attack first, and then the nucleophilic attack. You get a final product. Now, what's your responsibility in this chapter is to remember what are the reagents that changes, for example, alkene to alcohol, or alkene to alkyl halide, or alkene to ether, or alkene to glycol, or other examples that we do have a table for it, and we cover every experiment, every reaction one by one. So what are the concerns? If the reactant is given and the product is given, you need to know what is the reagent. If the reactant and reagent is given, you need to know what is the product. If the product is given, you should be able to say which 2 reactants actually gave that product. So that's a chemical reaction. That's knowing reactant, product, and reagent. Your other concern should be if the addition, if the alkene that you start with is a symmetrical alkene. So if you have a CC double bond, let's say, that is attached to a CH3 here and a CH3 on the other side, when you bring HBr, does it matter for hydrogen to attach to carbon 1 or carbon 2? If it's symmetrical, no, it doesn't make any difference. But if the carbon-carbon is not symmetrical, then it's going to make a difference. H is going to attach to 1 and Br would attach to the other one, specifically with the direction that the reagent you are bringing in is going to tell, based on the stability of the intermediate. So what is intermediate? Intermediate is when you bring the electrophile and you end up with the carbocation here. This is one kind of intermediate. Intermediate is a species that forms in a reaction and then it's consumed right away. You see, in step 1, it forms, and step 2, it's consumed right away. Intermediate cannot be separated, cannot be isolated, cannot be purchased. Intermediate is unstable. So some intermediates, so when you have unstable or very reactive species, then you have to decide between the 2 unstable species, which one is more stable, which one is better. So if you have tertiary carbocation, it's going to be more stable than secondary carbocation, more stable than primary carbocation, more stable than methyl carbocation. So when there is a point of difference that if electrophile adds to carbon 1, you would get more stable or less stable, that is going to make a huge difference in the direction the electrophile is going to go. So it's not free to go either carbon 1 or carbon 2. So if you have a hydrogen attached here only, and you have CH3 attached here, so it's going to make a difference, and it's going to make a difference, and the hydrogen, basically, the electrophile is going to add specifically to this carbon. The electrophile would add to this carbon, and the other carbon, which has more carbon bond to it, is going to gain the plus charge. Because, and I will show you that, since you have watched the video already, I can say this, but it's better when I show it. So I'm going to wait for the reaction, or for the slide that actually just mute my device here. So you have the point of difference. If it's unsymmetrical, if it's asymmetrical alkene. Okay. These are some of the examples. If you add water, okay, what you need to know also the name for this reaction. If you add water, the addition reaction is called hydration. Okay, hydration, just simply adding water. You add H2, the reaction is called hydrogenations. And if you add hydroxyl group, OH, 2 OH groups, 1 to each carbon, is called hydroxylation. So you need to know the reagent for hydration. You need to know reagent for halogenation. You need to know the reagent for hydroxylation, a specific reagent for it. But general name, if you're adding water, is hydration. You add H, you add OH. If you add halogen from group 7A, you add chlorine, Cl to each carbon, or Br to each carbon. The reaction is called halogenation. So formation of a halohydrin, that means you add halogen and you also add water. So when you add hydrogen and you add water, is a formation of halohydrin. HX addition is the product is going to be alkyl halide, cyclopropanation, and then epoxidation. These are some of the reactions. So what's important for you to make a table, memorize the reagents. Know what reagent is going to change alkene to alkane, and what reagent would change the alkene to alcohol. So what are the elements added, okay? And does it need catalyst or it doesn't need catalyst? So you have to look for all the conditions. Okay, when you have HBr, I already talked about this. I'm not going to spend too much time on it. So H comes in first, carbocation forms, then Br comes in. Your net result is formation of alkyl halide. In general, when you have electrophile and the nucleophile, electrophile would add to one carbon, nucleophile to add to the other carbon. So you have a net result of the addition. If your alkene is not symmetrical, okay, if it's symmetrical or if it's not symmetrical, is going to make a difference. In this case, this is just example. When you add HCl, H would add to one carbon, Cl would add to another carbon of the carbon-carbon double bond. The pi bond will break and two new sigma bond is going to form. One sigma bond carbon with hydrogen, the other one with the, but what do you notice here? That you have CH2, CH2, it's symmetrical. This side of the molecule, the right side of the molecule is same as left side of the molecule in 2,3-dimethyl 2-butene, So this is a symmetrical alkene. It's not going to make a difference at all if H is added to carbon on the left side or the carbon on the right side. Whatever carbon H is added, the other carbon will take the Br. Another symmetrical situation, whichever carbon takes the H, the other carbon will take the I, and it can be switched around with no problem. So the difference comes in when you have asymmetrical. What happens if you have asymmetrical alkene? This is not a symmetrical alkene. So H is going to come in first. If H attaches to carbon 1, Cl will attach to carbon 2, and that is going to give you product 1. If H attaches to carbon 2, okay, if H attaches to carbon 2, then Cl has to attach to carbon 1, and that would be a product. You're getting two different products. Whenever you get two different products, there is a question, which one is the major product, which one is the minor product? And then there's the explanation why the major product is major product. So whenever there is a chance for multiple products, then it's more challenging because you have to decide at that point which one is the major product. The question can ask you what's the major product, or it can ask you write all possible products. So what the difference is, if hydrogen attaches to carbon 1, carbon 2 will get the positive charge. So if hydrogen attaches to carbon 2, carbon 1 will take the positive charge. So we have this situation, this explanation right here. This is addition of the hydrogen to carbon 1. So if hydrogen attaches to carbon 1, basically you are getting this product. Okay, this product. The arrow I just have to make sure that you don't get confused with that. The arrow is coming from pi bond to the hydrogen. If the hydrogen is going to attach to carbon 2, then you get the carbocation on carbon 1. What's the difference? You have a secondary carbocation, you have a primary carbocation. What is the rule that you need to know by heart? That more stable carbocation is going to give the major product. Which one is more stable? What is more stable, secondary carbocation or primary carbocation? Because the secondary, in this case, actually, I'm just take it back, is a tertiary carbocation. Tertiary carbocation versus a primary carbocation. A tertiary carbocation is way more stable than primary carbocation. And if it was a secondary and primary, you would get both of them. But if you get tertiary, competition between tertiary carbocation and primary carbocation doesn't have a chance. It's not zero. It says not formed, but the concentration of this or percentage of the product formed is going to be very, very low. And this product where hydrogen is added to first carbon and Cl is added to carbon 2 is going to be your major product. So what other thing that you notice here in the molecule, one carbon has more hydrogens, carbon 1 has 2 hydrogen, and carbon 2 has basically 0 hydrogen. The rule that it will be discussed soon is like hydrogen, when you are adding HX, hydrogen will add to carbon with greater number of hydrogen. And so you have 2 hydrogens here and 0 hydrogen on the carbon 2. So hydrogen will add to carbon with greater number of hydrogen, and the Cl would add to the carbon with least number of hydrogen. The term is called rich gets richer, and also is called a Marconica product. Okay? But so if there is if your alkene is asymmetrical, then you have to look for one major product versus a minor product. And what makes the major product to be the major product is the stability of the intermediate that is forming. When electrophile comes in, you will get intermediate. How stable is that intermediate? If you have a choice of two intermediates like this, if you get a tertiary carbocation versus a primary carbocation, it's a clear cut and know that tertiary is going to be more stable, and more stable intermediate, major product. More stable intermediate, that means that you have lower activation energy. That means that that is going to form faster, and then that would yield to product much faster.
Professor, what happened with the chloride in the first one, in the third?
Okay.
And where it says third butyl cations, I'm like, what happened with the chloride?
In both of them.
No, in the first one, no, in the one that is on the top. Down below.
One?
No, down below.
Here?
Above.
This one?
Yes.
Okay. The chloride will come in and form bond with carbocation. That is the next step. The next step is that chloride would come in and form bond with where the carbon is positive charge, and that chloride happens right here, T-butyl chloride.
So basically in the first one, I don't know where it's located. Like,
You don't, can you follow my pen?
Yes.
Okay, that's chloride, right?
Oh, okay.
Okay, very good. Okay, stability of carbocation, we talked about this already. Any questions? A tertiary is more stable than secondary, than the primary, than the methyl. Okay, so when there is a chance or when there is a difference or asymmetrical, when you are dealing with asymmetrical alkene, you get a chance for different degree of carbocation. You could get secondary versus primary or primary versus tertiary, like you saw on the example. So when you have the carbocation formed, you have to see which carbocation is more stable, and that is going to yield to major product. Now, since we are talking about carbocation intermediate, we're talking about the stability of carbocation. But if your intermediate is free radical also is intermediate, like we saw in chapter 4, it's an intermediate, it's not a product because it's not stable. If it's stable, it has to be neutral. All the carbons must have 4 bonds and no negative charge or positive charge in the molecule. So anything that has positive or negative charge is considered to be intermediate. And for intermediate, you have more stable or less stable, and they're all very reactive and they're all unstable because you cannot keep them as the compound or as the product. It has to go through another cycle or another step of the reaction to change the product before we can isolate it. Okay. So more explanation or the example about that, when you add the HCl, you have 2 choices. If hydrogen adds to carbon 1, you would get 2 chloropropane. And if hydrogen adds to carbon 2, chlorine would add to carbon 1, and you get 1 chloropropane. The slide here, it says this doesn't form. I say the chance for formation of this is very low because primary carbocation is very unstable. But to make it like more significant, it says like this is not even forming because it's a primary. What makes this to be a major product to chloropropane? You have to go a step back and look at the intermediate. For the intermediate, you have your carbocation as a secondary carbocation versus the other case when hydrogen goes to carbon 2, the first carbon will take the plus charge and you have a primary carbocation. The more stable carbocation would yield the major product. Primary carbocation is very, very unstable. And that's why it just says is not going to form. And if this carbocation doesn't form, then there is no primary carbocation for HCl to attack. So no product of that is going to form. Examples of asymmetrical. So with this, you should be pro now, like you should identify H will attach to which carbon, carbon A or carbon B. This is for explanation of the formation of a carbocation. Otherwise, the attack should always go from pi bond to the H plus. If hydrogen goes to carbon on the isopropyl part, this one, a carbon 1, I would say, if I call it 1 and then 2, if H goes to carbon 1, carbon 2 would take the plus charge. And if H goes to carbon 2, carbon 1 would take the plus charge. So you have to know that by heart. When you have carbon-carbon double bond, you bring H plus, one carbon takes the H plus, the other carbon would take the positive sign or a positive charge and becomes carbocation. So if H comes to carbon 1, this would be your product. And if H comes to carbon 1, this would be the plus charge here. And then iodine would go to that carbon, you would get 2 iodine. If H goes to carbon 2, then iodine comes into the carbon, iodine would come into carbon 2 or carbon 1 designated, but in the molecule is carbon 2, this carbon, okay? Iodine would come to that carbon. And since this is going to be a tertiary carbocation, is going to be more stable and you would get a major product. So you have a minor product and you have a major product because it's secondary. So they actually write this as the minor product. If it's a primary, you can assume that it's not going to form because the percentage of that is going to be very low. Now, only when it's asymmetrical alkene. This is your alkene. What makes this asymmetrical? One side of the alkene functional group is attached to only CH2. The other side is attached to CH3 and CH2. So this carbon has 1 hydrogen. This carbon has 0 hydrogen, no hydrogen. The hydrogen is going to add, for major product, is going to add to carbon with the greater number of hydrogens. And that is known as the Marconica Rule. So you get your major product here. The other carbon, which has less hydrogen, is also known as more substituted carbon. And the more substituted carbon, when it gets the plus charge, is going to be more stable carbocation. So if the carbocation forms on the more substituted carbon, it's going to be more stable. So hydrogen should attach to least substituted carbon. If the carbon is least substituted, that means it has greater number of hydrogens. So you have to just know those terms like perfectly. Least substituted means it has more hydrogen. More substituted means has more carbon bond. So if it's more substituted and it gets the plus charge, it's going to give you like higher order of carbocation. Okay, the difference here is going to be a primary carbocation versus secondary carbocation. Secondary carbocation is more stable, and that's why chlorine would go to this carbon, because hydrogen should go to this carbon 1, hydrogen should go to carbon 1. When hydrogen goes to carbon 1, the plus charge is going to form here, and then you would get secondary carbocation. If hydrogen was in second carbon, if this happens, then you would get the plus charge here, okay? Then the plus charge would be on this carbon, which is not stable, and that's why it's not happening, okay? You would get a primary carbocation that is not stable, and that's why it's not happening. Any questions? So you have to decide if you are dealing with asymmetrical alkene, which one would take the electrophile, which one will take the nucleophile. And here it's showing like in stepwise, if hydrogen is attached to this carbon with greater number of hydrogens, then the plus charge would be on the more substituted, and we get a tertiary carbocation. If hydrogen is attached to the carbon with the least number of hydrogen, then the plus charge would be on the carbon with more number of hydrogen or lower substitutions, and you get a secondary carbocation. Between a tertiary carbocation and secondary carbocation, tertiary is more stable than secondary. So this would be, tertiary is going to yield major product and secondary would yield to minor product. There is also a chance for rearrangement. In this case, there's a chance for rearrangement when carbocation forms. When carbocation forms, then there is a chance for rearrangement. That means the hydride shift. But let's look at the Marconica addition or the rules first before we go to the to rearrangement. So electrophile would add to least substituted carbon. So electrophile to the less substituted end of the double bond. And then as a result, the nucleophile would add to the other carbon that has more substitutions, and that would give you the major product. The other one is not happening because it's not stable. Okay, so if you're writing one product, just write the major product. So if you have a more substituted carbon here, hydrogen would add to least substituted, Br would add to more substituted, and you have one product. If you are given more than one product, then you have to get the justification based on the intermediate and take the major product from the intermediate that is more stable. So if you get hydrogen to carbon 2, so this is a carbon. So you have a carbon 1, 2, 3. So what would be the 4 if this is the product? I said the other type of questions that reagent is given, product is given, you should write the reactant. What should be the carbon-carbon double bond that would yield to this major product for you? So if you have 2 possible alkene that would yield to this, both of them would yield to this this product, the 2-hexane or 3-hexene, sorry. So with 2-hexene and 3-hexene, which one would be a better choice? 3-hexene is symmetrical, 2-hexene is asymmetrical. So if you give it asymmetrical, then you are giving a chance of formation of 2 separate products, 2 different products. But if it's symmetrical, it would yield to only 1 product. So I would take the one that is symmetrical because I would get 100% of this product if I use a symmetrical alkene. So basically it's trying to elaborate or make you think and understand the difference between the symmetrical and asymmetrical. If you have a choice of 2 products versus 1 single product, you should always go with the 1 single product because 100% of the product would be that type. And if you only need one of the 2 products that is possible, even if it's like one is more stable than the other one, you still have impurities to deal with, and you have lower, so because part of the product would go to the site that you don't need it. It's like unwanted product. Questions, because these are all repeating. Questions? No questions? So with all these examples, says that we would get a Marconica product. What is a Marconica product? Is when hydrogen adds to a carbon with more number of hydrogen, or rich gets richer, and the other one, the nucleophile, would add to the other carbon. Now, if we have a Marconica product, we also have anti-Marconica product. And what would you do for anti-Marconica product? Or if you like to get anti-Marconica product, you have to change the mechanism of the reaction. So carbocation cannot be your intermediate anymore. You have to change the mechanism of reaction in a way that you should get a more stable intermediate when the hydrogen is added to more substituted carbon. So the addition of the HBr, if you add a catalyst of peroxide, so when you add peroxide, the product is going to be anti-Marconica. Peroxide, if you know hydrogen peroxide, H2O2, alkyl peroxide, the H2O2 is like HO bond, like this. You have oxygen, oxygen, single bond in the molecule. It's very unstable. It can break through hemolytically easily, and it can give you free radical of HO, two of them. And alkyl peroxide is very similar to that. So whenever you have like alkyl products, peroxide used as a catalyst, or anytime in the reaction mixture you see peroxide, that should be a hint. By the time you finish chapter 8, there's a lot of reactions, and with all those reactions, when there is the peroxide involved in any step of the reaction, the product is anti-Marconica product. So if you have the peroxide is going to generate free radical, which is going to form one with the HBr. And for this one, HBr, for this reaction, when you bring the peroxide, only HBr from comparing to HCl has a right energy, so it will work. So we don't usually use the HCl for this, we use the HBr. So with the HBr and the free radical of the alkoxy free radical, you would get alcohol and then free radical of bromine free radical. Now, your bromine free radical is coming to attack the carbon-carbon double bond first, rather than the hydrogen. So basically what the proxy does, the alkyl peroxide does, is generates a active intermediate of free radical, bromide free radical or bromine free radical, that is going to attack the carbon-carbon double bond. Now, bromine, if it goes to this carbon that is least substituted, the other carbon would take the plus charge, and you get more stable. So you have a tertiary free radical here, a tertiary free radical. And if bromine comes to more substituted, then you get a secondary free radical. And if you get a secondary free radical, which one is going to be more stable? Again, is a tertiary, more stable than secondary, more stable than primary, more stable than methyl free radical. So it's just that mechanism is changing, and is not the hydrogen who's coming first, is the bromine that is coming first, and is generating more stable free radical. So your intermediate is changing. Instead of the carbocation, now you have free radical. So when you have a choice of a tertiary free radical versus a secondary free radical, tertiary free radical would be the major product, and the secondary is less stable and it's not forming as the major product. So your major product is going to be, when you add the hydrogen later, then you see that hydrogen is being added to more substituted, bromine is added to the least substituted, and this is known as anti-Marconica product. Okay, other addition reactions. We have plenty of addition reactions, but I just want to make sure that you learn about the difference between a major product and a minor product. The rest of these reactions, they are very similar. And since you already have a recorded lecture of it, it would be easier for you to follow. So some reactions, they require, like this one, addition of water is going to require catalyst, because you don't have basically electrophile that pi bond is going to attack here, because water does not dissociate. It does dissociate, but 10 to negative 7 molarity, so it's not dissociating. The self-ionization of the water, because it's a neutral compound, is going to give you very low concentration of H+. So since you don't have a reason for this pi bond to attack the water, is you have to get the catalyst. Catalyst is the species or is the reactant that is not going to be consumed or is in the reaction, or is going to be consumed, and then it will generate again. So in hydration of water, you have to use catalyst, but for HBr, addition of HBr, because you already have the H+, the reactant act as a reactant and as well as catalyst. So HBr comes in first, then Br minus comes second as a nucleophile. What type of addition is this addition? Marconica or anti-Marconica? What do you see here? Marconica or anti-Marconica? Marconica, because hydrogen is added to carbon with greater number of hydrogen, and OH is added to least number of hydrogen or more substituted carbon. So addition is going to be Marconica. So if the hydration, we have 3 types of hydration, we have to be more specific about it. If the hydration is a direct hydration, that means you just add water and acid. So this is acid catalyzed hydration. The product is going to be Marconica addition. In the Marconica addition of direct hydration, you will get formation of a carbocation. Okay, carbocation forms, and then it goes to the product. So in step 1, you will get formation of carbocation. So carbocation forms is not from the hydrogen that is coming from water, but this hydrogen that came from acid. It formed the carbocation. And as long as carbocation forms, or if the hydrogen is added, it really doesn't matter hydrogen is coming from acid or is coming from water. Is not going to recognize it unless you tag your hydrogen. You use like deuterium instead. But on the next step, this is what I was talking about, that your nucleophile doesn't have a negative charge, is neutral. When you bring a neutral nucleophile in, the H2O adds at O, the carbon attached to the oxygen. So you have an OH and still another hydrogen attached to it, but it's going to take over this plus charge. This plus charge is going to be transferred between carbon-oxygen bond, or still is on the oxygen. And oxygen, because it's highly electronegative, does not like that plus charge. it's a disaster. It's like the worst thing you could do to oxygen, to give it plus charge, because it's highly electronegative. So there are two solutions. When you see like OH2 with the plus charge on it, there are two solutions. One, to remove one hydrogen with the plus charge. So if you remove a hydrogen with the plus charge, you only left with the OH, and H plus is gone. Okay, H plus has been removed by the water, like by the solvent in this case, is removed. The other solution is going to be remove H2O and leave the plus charge back. But if you do that, it would basically take you to the previous step. You get carbocation and water, and is not beneficial. So it's not going to happen in this case, because carbocation is very unstable. It wants to attack to the carbon. It wants to react with the carbon and give this. So next step, when you remove the hydrogen using a base or using the solvent, you are going to end up with OH. So when you see you have a neutral nucleophile that you are bringing in to add to the carbocation, there's additional step that you have to take care of, removing of the plus charge. You have to overall end up with the neutral compound. Addition is Marconica addition, because H is added to carbon with two hydrogen, and OH is added to carbon with one hydrogen. This is a Marconica addition, is also known as direct hydration. Hydration means adding water. What happens if you add alcohol? Whenever you add alcohol, just like adding water, like adding alcohol, CH3OH is example of the alcohol. That means you add H and add CH3O, just like hydroxide and hydrogen. In this case is alkoxide and hydrogen. Alcohol also is not very reactive, and because it's not very reactive and it doesn't have H plus, because we are basically, when we are adding alcohol, we are adding H plus and the CH3O minus. Okay, that's the net result. Since there is no H plus here, it doesn't ionize, it's not a strong acid, it doesn't give H plus. We have to bring a catalyst first. So you bring a catalyst to protonate the alkene, to create the carbocation, and then the next step. So you get the H plus coming first. So when the H plus comes in, you can protonate the alcohol to give you more reactive hydrogen now here. So this is a strong acid, very strong acid. So CH3OH is not an acid, but if you add proton to it, CH3OH2 with the plus charge, this is a strong acid. Now the pi bond can actually come and remove one hydrogen or attack the electrophile from this protonated alcohol. So you can see that carbocation is forming. When the carbocation forms, your nucleophile is a neutral nucleophile. When the nucleophile is neutral, after it forms bond with the carbocation, you have to deal with this plus charge again on the oxygen, which when you bring the solvent to remove that H plus, you end up with net addition of the alcohol. H is added to carbon 1 and OCH3 is added to carbon number 2. When you have formation of a carbocation, I talked about rearrangement, possibility for rearrangement of the carbocation. And when does the rearrangement takes place? It's always going from, if you have a primary carbocation, and as a result of rearrangement, you would get like a secondary, or you would get like a tertiary carbocation. From secondary to secondary, it doesn't happen. From primary to primary, it doesn't happen. From like secondary to primary, definitely is not going to happen. So what is the rearrangement? Let's say if you have a CH3 here and you have CH2, CH2 plus, okay? This is a primary carbocation. Now, in this case, you do have a hydrogen on adjacent carbon, okay? You have this hydrogen on adjacent carbon. Okay, what happens if this hydrogen moves to carbocation? And when it does move, it's not going to move as a H plus. So we do have hydrogen, we have hydrogen ion, we have hydride ion. It takes ID ending. This is a hydride ion. So if this is a hydride shift, that means hydrogen with pair of electron moves to carbocation. What happens to the other carbon? Now this carbon, if it loses 2 electrons at the same time that it's losing the hydrogen, is going to gain the plus charge. So this plus charge is going to move here. This is called rearrangement. When does rearrangement takes place? When you have a hydride, available hydride on adjacent carbon that is going to be available to move and transfer the plus charge. So that's one condition, hydride shift. Hydrogen is not very heavy, so it takes less energy compared to other groups or methyl group, but it does happen if degree of the carbocation is going to change from primary to secondary. This definitely is going to take place. So that was one condition. Second condition, if you have a methyl group attached here, let's say you have a methyl group, and with that methyl group, you had a plus charge on carbon 1. There is a methyl group here attached to the carbon adjacent to the carbocation. In this case, you would get a methyl shift. So methyl group with the pair of electron is going to shift to carbon 1. And since as a result of this shift, this carbon is losing electron, carbon is going to gain plus charge. So that is called a methyl shift. So what's going to happen in this methyl shift? Your carbocation from primary is going to change to tertiary, and that is a big deal because it's a lot more stable. So when you look at the examples that is on this slide, you start with 3,3-dimethyl 1-butene, and you would expect, okay, you already learned about Marconica products, so hydrogen has to go to this carbon and chlorine has to go to this carbon, and then you look at the final product, that's not your product. Your product is this. How did that happen? What made the chlorine to go to the third carbon is, first of all, you had the hydrogen coming to this, carbocation formed on the second carbon, but since neighboring carbon had the possibility of formation of a tertiary, there was a methyl shift, the methyl moved up, and you get a tertiary carbocation. So basically, this is like a rearranged carbocation. So you get rearranged carbocation, and as a result, you get a product that is not expected. But now that you know if there is a carbocation, there's a possibility for rearrangement, you should always look for that product as well. So we learned about hydride shift, and we also learned about a methyl shift. Okay, so hydride shift or methyl shift. If there is no hydrogen on adjacent carbon, there is no methyl group on adjacent carbon, there would be no shift. It's not going to take place. And what makes this product to be a major product is because your carbocation is a tertiary. A minor product comes from a secondary carbocation. And the shift will only happen when you get a more stable carbocation. Shifts between secondary and secondary carbocation is not gonna happen. Sometimes the shift is going to even cause a opening of the cyclic system. Is not just the stability of the carbocation in this case, is actually instability of the cyclic form. Cyclobutane, if you remember from chapter 3, cyclobutane with the 90-degree angle, it's very susceptible to ring opening because it's not stable. And on the neighboring, you have like a secondary carbocation that can change to a tertiary carbocation if this ring opens, and it does open and it gets the tertiary carbocation is generated. Okay, questions?
No questions.
No questions. Okay. They paused the recording.